Okay, yesterday we talked about sampling distributions in the context of averages, right? And there's another big topic in there, and it's sampling distributions with proportions, which is another word for fractions or percentages. So when you're talking about chapter 8 material, you got to ask yourself, am I dealing with an average or a proportion? And the problem will make it pretty clear. So take a look. It says, if we've got a random sample of size n from a population in which each individual either has or doesn't have a characteristic. Now then, what do they mean by that? They mean, okay, how many people are in favor of this proposition? Or how many people think we ought to paint this room? Whatever. That's going to be a proportion. Me too. That's going to be a proportion. It's not an average. It's like what percentage of folks don't pay their taxes on time or whatever. So that's what we're talking about here. And notice that for that, you get a sample and you say, well, let's say we get a sample of 100. Well, how many people out of that 100 believe in the Easter Bunny? And so we get a certain number. So let's say 60 people out of those 100 believe in the Easter Bunny. Then that proportion would be 60%. Or 6/10, however you want to put it. But it's still a proportion. It's not an average. And notice what they're calling that proportion that you get from a sample, p hat. So it's that p symbol with a little hat on it. And that means the statistic you got from taking that sample. Now, if this were a mean, we'd be saying, well, that's x bar. So this is the equivalent to x bar when we're talking about proportions. And notice it tells you how to get it. You just divide how many people or things have that characteristic, and you put it over how many things you had. There that is right there. So that tells you how to get p hat. So p hat, as this is telling us, is a statistic. Bless you, multiple times. And what are we doing? We're going to try and use that to estimate something about the population proportion. Y'all, the population proportion is the letter P. Please notice that. So if you have to write yourself a note, if you just see P, think population parameter. In other words, is there such a thing in the state of Texas? Is there a certain percentage of people that believe in the Easter Bunny? Yeah. Will we ever know it? No. But we can get a sample and get an estimate of that. As we do with most distributions, we're looking at three things. The shape. Is it skewed? Is it symmetric? Is it normal? Where the center is and what the standard deviation is. We've done that on every distribution we've looked at. All right, here is the main little box about what a sampling distribution of p hat is. This is way different from a mean. Don't get those confused. So the shape of it is about normal as long as when you multiply the sample size times the population proportion times 1 minus the population proportion, as long as you get a number greater than or equal to 10. All that really is saying is our sample large enough? See, if you got a small sample, when you multiply those three numbers together, you won't get a number bigger than 10. Notice where the middle of the sampling distribution is. Again, we've got two distributions. We've got the population distribution and we've got the sampling distribution, just like we did with means. So the mean of this sampling distribution is exactly the center of the population. And if you remember from yesterday, with a population of any size at all, will we ever be able to get a true sampling distribution? No, just impossible. Look at the standard deviation formula for the sampling distribution of p hat. The square root of p times 1 minus p divided by n. Totally different from what an average is. Down at the bottom, I highlighted it. You have to get your sample randomly. No standing on the corner and just asking people as they walk by. And the second thing is those values have to be independent of each other. And we see that 5% rule again. In other words, if your sample is 5% or less of the population size, we're going to assume independence unless something else tells us different. So those three things are just like with a mean sampling distribution. And then the last thing down there says, we don't care about the shape of it in the sense of where the center is and what the standard deviation is going to be the formulas that they gave us. The shape is going to be governed by what? That NP times 1 minus P being greater than or equal to 10. Okay, so there's our reading material. All right, it's got to be random. It's got to be independent. Don't forget that. Let's look at some examples here. Not as much explaining to do this morning because we covered a whole lot of that yesterday with what a sampling distribution is. So in a town of 500 households, 220 have a dog. What's the population proportion of dog owners? How would I get that? Exactly. And then I can reduce that to a decimal if I want to. So in other words, we'd say in this town, 44% of people are dog owners. That's not an average. That's a proportion. Number 2, a 2-worded answer. Denoted p hat is given a formula. Okay, so that would be the sampling or the sample proportion. And we find that how? However many people or things have that characteristic we're looking for. What proportion of people in this room right now are blonde? What proportion of people in this room are wearing yellow shirts? You could make it about anything, but you just take however many match that characteristic and put it over the sample size. All right, true or false? The population proportion and sample proportion always have the same value. Remember, the sample proportion is what we got from the sample. Is it always going to have the same value as the population proportion? What do you think? I agree. Number 4, the mean of the sampling distribution of p hat is p. Yeah. The center of the true sampling distribution is the same as the center of the population. All right. Describe the circumstances under which the shape of this sampling distribution of p hat is approximately normal. Well, what has to be true? That formula. If that's true, we're going to assume that our sample's large enough for our sampling distribution to be normal. And we want that because we can use z-scores and we can use that table and we can do all sorts of the math that we've grown to love so much. Number 6, what happens to the standard deviation of p hat, that's the sampling distribution, as the sample size increases? Well, what happened yesterday? Yeah, standard deviation decreases. And the last part of that question, if the sample size is increased by a factor of 4, meaning now it's 4 times as big, what just happened to the standard deviation? Yeah, once again, thank you, ma'am, it got cut in half. So it's kind of a Goldilocks thing. We want a sample big enough that we have a small standard deviation, but small enough that we can consider the things in the sample independent. Is any of this going to change the shape of the population? No. All right, let's look at problems 7 through 10. Talking about the sampling distribution of p hat. So number 7, our sample size is 500, and the population parameter is 0.4. So what's the center of the sampling distribution? Same as the population. The standard deviation. How do we get it? Okay, with a few minor corrections. That's what we got on this one. How about the next one? There's the middle. I think I might have gotten this one right even. I'm getting 63 for the number, and since that's greater than or equal to 10, normal. Number 9, where's the center? Exactly where the population center is. Standard deviation. I mean, once you've seen one of these, you've pretty much seen all of them. All right, and since I'm getting 92 point something, that's bigger than or equal to 10, so I know normal again. So what have we just covered there? We've covered the center, we've covered the standard deviation, we've covered the shape. Now, if you get a number out there on the shape part, less than 10, what does that tell you? Your sample's not large enough to be able to assume that the sampling distribution is normal. So our last one here, the center is at 84.84. Here's our standard deviation. What shape are we going to get on this one? So all of these lead us to think that those distributions are normal. Again, not the population, but the sampling distribution. Are we good so far? So far, it's just been plug and play, right? Let's look at some real problems. Okay, we got a sample of size 200, and it says it's random, so that's good. They do tell us about the population. Is 200 less than or equal to 5% of the population? So it's random. Let's see. So I divide 200 by 25,000, and I'm getting 0.008. Well, that's way less than 5%. We know it's random, so we met our 2 conditions to be able to do this. So always check those, because we might get a quiz or something that's not true, and you'd go, well, I'll figure the answer out for you, but I can't promise it's accurate because we didn't meet the conditions. Okay, it wants to know, describe the sampling distribution. Well, where's the center of this thing going to be? Wherever the population is. So 0.65. And that says mu of p hat, so the center of our sampling distribution. Okay, how about the standard deviation? We just plug it into that formula again. And again, if you need a decimal number, just get it, but there's the formula for it. So all of these things are talking about the sampling distribution, not the population. Okay, so there's to 4 decimal places what that worked out to be. How about the shape? See what you get. Here's what I got. Once I see a number bigger than or equal to 10, I'm golden. I don't care how much bigger it is. So we think the shape is probably approximately normal. Now we get into a probability idea. What's the probability of getting 136 or more individuals with this characteristic? Whatever it is. They don't tell us what the characteristic is here. It could be people with earrings out of a population. Who knows? So the first thing I'm going to do is make a drawing. There's p hat, right? X out of 200. So 136 out of 200. So 68%. Here's my drawing. Okay, notice I've got 0.65 dead center because that's where the mean is. And then I'm looking at 0.68, so I make a little line for that. And then I look at the problem and I'm looking for 136 or more. Now notice I'm not seeing in my drawing the number 136 anyplace because I want proportions in my drawing. So I colored that blue. That tells me what? Whatever I get from the table, I've got to subtract from 1. That little drawing will help remind you of that. So I get a z-score. And I'm just using the number I got up there, 4 decimal places. That's fine. I get a z-score of about 0.89, which gives me this probability. And look at the notation. Don't want to see just a number sticking out there. I'd like for you to write it just like this. The probability that x is greater than or equal to 136 is, and then show me that much work. I know you're going to do it on a calculator. You'd be crazy not to, but. All right, take a look at C. What's the probability of obtaining x equals 118 or fewer? So I get my sample. What's the probability of that sample having 118 or fewer people with this characteristic? So first of all, I get what p hat is, 0.59. Next thing, I highly recommend making a drawing. So there's my 0.65 in the middle again. And I'm seeing 5900ths to the left of that. Now this says 118 or fewer. So that 0.59 is where 118 out of 200 would be, right? Which side do I want to color? Left or right? Left. So I color that in. So now I can just look it up in the table. So I get a z-score. Again, just using the standard deviation I got from part A up there. And I'm getting this for a z-score. Negative 1.78. So that's almost 2 standard deviations away from the mean. So I'll look it up in the table. And that's what I'm getting. So the probability that with that distribution, I would get 118 or fewer people with whatever characteristic we're talking about is less than 4%. So not real likely. Different from the means that we talked about yesterday. Still a sampling distribution, but what does that indicate? Well, on these kinds of problems, when they're all mixed together, you got to say, am I talking about a mean or am I talking about a proportion? Decide that right up front. Are you satisfied? No, let's not even go there. The proportion of Americans who are satisfied with the way things are going in their lives is about 82%. So that means out of 1,000 people, 882 would be going, yeah, I'm okay. Suppose we get a sample of 100 Americans and ask them that question. Is this a quantitative thing or a qualitative thing? Whoa. Because? Quantitative why? Are you satisfied? Are you not satisfied? Are you male? Are you female? Are you Catholic? Are you not Catholic? That's, yeah. But it's more categorical than it is quantitative. So let's go with go with that. Now that was not true with the averages, right? With averages, it was all quantitative. Yet another difference here. So either you're satisfied or you're not. Explain why the sample proportion p hat is a random variable. Well, what would cause the randomness in this thing? I just got a sample of 100 people. Okay, the very people that I chose. What if I got another sample of 100? Would I get the same responses, do you think? Probably not. Probably not. So it's just the randomness of the group that we got. P hat, that proportion from the sample, is going to change each time we do it. Then they want us to describe the sampling distribution of p hat. Okay. Was this random? Yeah, told us that in part A. Is 100 sample size smaller than 5% of the population of Americans, do we think? Yeah, I think we're covered there. So we're good as far as the conditions go. So where's the center then? So we covered those two things. Where's the center? Well, at 0.82, because they told us what the population parameter was. The center of our sampling distribution is going to be right there. How about the standard deviation? Well, we use that formula. And then shape. Here's what I'm getting. 14.76, so I know that's greater than or equal to 10. So the shape is approximately normal. Okay, example 4, we're keeping on here with our sample of 100. What's the probability that out of those 100 people, at least 85% of them are satisfied with the way things are going? Well, we already know it's random and it's less than 5% of the population, so I can do what? Make my little drawing. And the question says, what's the probability the proportion is at least 85%? Everything after that. What does at least mean? 85% or more, that's why I'm out there right there. Watch out for things like at least and no more than. Those will trip you up. Make sure what you shaded is at least 85%. Yeah. Greater than or equal to. All right, so I've got my drawing. That means with the way I shaded it, I've got to subtract whatever I find in the table. I've got to subtract that from 1. So, as we've done so many times, we get a z-score here. And I just put the formula down there. If you want to get that to 4 decimal places, you could. So I'm getting this for a z-score. Is a positive number, is that at least reasonable with what we're looking for here? Well, yeah. We're on the right-hand side of the mean. So I'll look this up in the table. And again, notice the notation. The probability that p hat is at least 85% is 1 minus what I found in the table, which is this. What does that mean? It means if I got a sample of 100 Americans and did it right, that the probability of that sample having at least 85% of the participants being okay with the way things are in their life is just a little less than 22%. Now, that said, look at part E. Would it be unusual for a survey of 100 Americans to reveal that 75 or fewer? Now, look what they're doing to you. They're giving you a number, not a percent. In part D, they gave you a percent to shoot for. Here, they're giving you a number. So what do you have to do? Yeah, exactly. You got to find the p hat. So I could have done it without the fraction, I think, but find that 0.75. Make your drawing. This says 75 or fewer. Now notice that 0.75 represents where 75 or fewer is. And so since it says or fewer, I color in that side of it. Okay, we're set up, we're ready to go. We get a z-score. And again, I just put the formula. Just to remind you, that's what it is. Here's what I'm getting. Now, just looking at the z-score, do you think this is very likely? No, because we're almost 2 standard deviations from the mean. So here's the probability. So less than 4% of the time would I expect to get a sample where 75 or fewer had this characteristic of believing that their life is okay. Yes, sir.
So why in part D did we say P hat and in part D we used X?
Because I needed the numerator of that fraction. See, that's a good question. In part D, they told us 0.85. They'd already done the work for us to get that. In part E, we had to say, well, 75 people out of 100, well, that was pretty easy. But what if it had been 75 out of 306 or something? Then we'd have to do that math to get the actual fraction. So we're comparing apples to apples. Good question. Oh, yeah. You're not going to get it incorrect, though. You're going to get it right. You are. All right. So we got some transistors being shipped in. And we've got a person that is the gatekeeper that gets a sample, and it tells us random, of 500 resistors. And he or she's going to reject the entire shipment if 10 or more of those 500 are bad. It's 10 or more out of 500 now. And then we're omniscient now, and we know that 4% of the resistors in the whole shipment are defective. Now, that engineer would not know that. Okay, what are we looking for here? Is this random? Yep, tells us so. Is 500 less than 5% of the population of transistors? Yeah, it's 1%. So we're good. We met our two conditions, but now how do we set this up? What's the probability this engineer accepts the shipment? Think of it like this. If out of those 500, 490 were good, is she going to accept this? No. Because it says if 10 or more are bad. So if 490 are good, she's going to reject. What would it take to get her to not reject? 491. So what I'm going to do is say, all right, got 96% good. So I want to get a fraction here. So if at least 491 are good, she's going to accept the shipment. So what am I going to get for p hat? How would I do that? I'm with you. 491 over 500. And that's going to give me, what is that going to give me? That's going to give me this. Now look at what we got, y'all. This 0.982 is p hat. In our omniscience, we know that 96% of these things are good. So what am I going to do for a drawing? Well, my 96% is right there in the middle. I'm hoping to get to 0.982 or better. So I color that side in. This one's tricky. So what does that tell me? I got to subtract what I find in the table from 1. But now I've got enough information to do my z-score. Can you do these in your sleep now? And when I actually get the z-score, this is what I got. Whoa, how likely is that? Not particularly. So the probability of having 491 good ones in that shipment is this. For a z-score at 2.51, the corresponding area to the left of that is 0.9940. So I have to subtract that from 1, and I'm getting this. Now, what does that tell you? She's going to accept these shipments from this company 6 times in 1,000? X is the actual count of good ones.
They didn't give us a percent.
Yeah, we came up with that percent. Now, y'all, suppose we're the manufacturing company that's sending these transistors to a manufacturing plant, and this person is rejecting 994 out of every 1,000 we send them. Are we happy? No. And so the last part of the question says, do you believe this acceptance policy is sound? Well, are they making a good decision? Well, okay, let's suppose a couple of scenarios. Let's say those transistors were going to go in little dolls that when you squeeze them, they cry. Is that an important thing? then that means this policy is probably too strict. But what if they're going into the space shuttle? Would we maybe want that policy to be pretty strict?
Yes.
If you're on that shuttle, you do. Because what was it that brought the Challenger down? An O-ring, a little rubber O-ring that cost 19 cents or something that failed. So it depends. So the answer to that question is, it really does depend. What are they being used for? Is it a critical kind of thing? If so, I might want them to be that picky. If not, might not want them to be that picky. So that's kind of a thought question there. Be that as it may, the engineers only accepting 6 out of every 1,000. One last little part here. Afraid to fly. Yeah, count me in there. The proportion of Americans who are afraid to fly is 10%. So we get a random sample, magic words, random, of 1,100 Americans. And out of those 1,100, 121 say they're afraid to fly. Now, is this evidence that the proportions changed since they took that poll? In other words, let's take a look. First of all, was it random? Yeah. Is 1,100 5% or less of the population of American flyers? Yeah. Easily. Okay, so it's set up right. So what's P hat here? Now look at this. P hat's 11%. The Gallup poll said 10%. Is this an indication that our proportion went up? Or is it enough evidence for that? I mean, it did go up for this one sample. But you got to get the idea in your head, maybe that one sample doesn't necessarily indicate that it went up. So what am I going to do? I'm going to get a z-score. And I'm getting this. Now, please understand what that represents. That means assuming that the Gallup poll was right and that it's still 10%, the probability of getting a sample to come out at 11%, there's my z-score for it. So I look that up in the table, make my drawing here. And which side am I looking at? That many are more, right? So one more time, I've got to subtract my results from 1. And when I do, I'm getting this probability. Stop right there. This is kind of a foreshadowing of chapter 9 stuff. Assume that the Gallup poll was right and that it really is 10%. Still, what's the likelihood of getting a sample where it's 11%? A little over 13. Is that unusual? No. Meaning, I could expect to get a sample that bigger or bigger, even if it really is 10%. I could expect that 13% of the time. So is this enough evidence to show that things have changed? No. Because why? Because we could get results this far away from what the Gallup poll said over 13% of the time. And like I said, we're going to be dealing with stuff like this a lot in chapter 9. That's it for the notes, y'all.